All right, y'all. Welcome to Stats at Home with Zared. So, recording this lecture for one-way ANOVA. So far in this course, we have covered quite a lot of ground. It might feel like it, or it might not feel like it, because we've only really talked about four different hypothesis tests: t-tests, single sample t-tests, dependent t-tests, and independent t-tests. But really, everything that we've covered so far is just an enormous amount of information, all about asking a very simple question. Does this mean differ from that mean? Right? Everything we've done so far is comparing two means, be that a sample mean to a population mean, as in the z-tests and the single sample t-tests, be that two completely separate sample condition means in the independent t-test, or be that the same group in two different conditions, as in the dependent t-test. So what do we do with experiments that have more than two groups, right? Not all, most psychology studies are going to be more complex than simply comparing this group to that group, or this group at this time to this group at that time, right? We often will do things that are quite a bit more complex, for which we need to learn some more complex analyses. And the last major family of analyses we're going to be learning is ANOVA. So there's two different kinds of ANOVA that we're going to be talking about. Maybe not exactly two different kinds. Two different ANOVAs for one independent variable and ANOVAs for two independent variables. This lecture is focused on ANOVAs with one independent variable. The next lecture on advanced ANOVA is going to be for ANOVAs with two independent variables. So for now, let's try to focus on what the question that we're trying to ask is. What questions are ANOVAs good for? And those are the types of experiments that have more than two groups, more than two levels. In the experiment that we've been using in lab, we focused on the distinction between Joan is neutral story and the Joan is angry story, right? Two conditions for which a t-test will suffice. But there's a second independent variable in that study, in which that we touched a little bit on in the data filters section of the dependent lecture, in which the appraisal information, the amount of information that readers had in the story, that's what the appraisal information means. The appraisal information was either that the reader knew no one was responsible for Katie's death, they knew that the warden was responsible for Katie's death, or they knew that Peter was responsible for Katie's death. So one independent variable, the appraisal information, what did the reader know about the situation in the story, with three levels. No one's responsible, warden's responsible, Peter's responsible. So that is firmly in the world of one-way ANOVA. One-way ANOVA, one independent variable with three or more levels. So most of the examples that we'll talk about have one IV with three conditions, but really you can have an infinite amount of conditions. I mean, you'll never have an infinite amount of conditions, but you can have as many conditions as your heart desires, because the math is pretty much exactly the same. It is looking at how much some means differ from one another and then dividing that by how much the means would differ by chance. Now, you might notice that that basic kind of distinction in the math is pretty much exactly what we've been talking about so far. Because for the most part, one-way ANOVA and t-tests at their core are exactly the same thing. They just compare a couple means. Now, the number of means differs, right? ANOVA, more than two means, three or more. T-test, two means. And but for our purposes, they're pretty similar. And so let's first, before we get into the different flavors of ANOVAs, let's talk about what's really different between t-test and ANOVA. Right? So let me pull my here. I get a little whiteboard. So t-test is, as you might remember, is a mean difference. I'm not as good drawing with a mouse as I am a marker. Over sampling error, right? That's what t-tests do. It subtracts one mean from another mean and then divides by sampling error. But with ANOVA, we have more than two means. So what would you subtract, right? It doesn't make a lot of sense to subtract mean 2 from mean 1, because what about mean 3? And it doesn't really make sense to subtract mean 1 from mean 2 to mean 3, because where's the difference actually going to be? We need something new. We need to just expand our framework of how these statistics are built just a little bit. Now, this math is a little bit more complicated than what we've been dealing with, but it is based on a bunch of things that we've already done this semester, which is add some stuff up and subtract some other stuff, right? That's what the statistics that we're talking about does. Subtract some stuff, add some stuff, divide by some stuff. All right. So the new concept to get you to think about what the ANOVA does is called between group variance. I guess before we go too much further, let's actually define. So with a t-test, when we conduct a t-test, we get a t statistic, a t value. But with ANOVA, we get an f, which doesn't make any sense because ANOVA starts with an A, right? T-test starts with a T. That makes sense. ANOVA gives us an F. And that's because the guy who invented ANOVA, his last name is Fisher, and we've talked about him a little bit before, mostly about how he's an egotistical jerk. So he decided to name the statistic after himself. And Fs are calculated by dividing between group variance. Oh my goodness, this takes forever. Between group variance over error variance. right? So the F ratio, the F statistic is a ratio of between group variance to error variance. Now, for the most part, this error variance is very much like what we've seen before. It is variance that is due to chance. Oh, I guess I can type. Right? So error variance is variance that is due to chance. And whereas between group variance is how much the condition means differ from one another on average. And now let's focus in on that on average piece, because you might remember the whole way back to the variability lecture that variance is the average of squared deviations. Right? Variance is the average of squared deviations. So remember, we calculated variance by taking some value, subtracting the mean, squaring that mean, adding all those squared deviations together, and then dividing by the number of people we have in our sample, the number of scores that we have. So it's an average because it divides by the number of scores, and it's the average of squared deviations because this is a deviation, x minus the mean, squared, that you sum. So that it's the average because it adds stuff up and divides by the number of things, and it's squared deviations because these are deviations squared. And so you'll notice that with the F, there's a variance in the numerator and there's a variance in the denominator. Now, we don't know what between group and error means exactly yet, but we do know something. Specifically, that all F's will be positive. F can equal 0 because if there's no error variance, there's going to be, F can equal 0, but it will almost never equal 0, really. So it can theoretically, but it might not usually. But the point is that F statistics can never, ever, ever be negative. And so all semester, I've been drawing this normal distribution, which it looks not terribly half bad, in which, that looks terrible, in which usually for t-tests, the mean of the normal distribution was when t equals 0 because t can be negative. But that's not the case for f's. Let's see, I can get it straight. There, that's a little bit. For f, the distribution looks a little bit more like this. Where it starts at 0 and it peaks at 1. Now we'll get to what that means in a little bit, and then it goes the whole way to infinity. That's the statistic. The F statistic is bound at the bottom at 0. It goes towards infinity, and the most frequent value is 1. Now, don't get too hung up on that part, but what I'm trying to point out here is that just like t-test, just like z-test, for every f, there is a corresponding p. That every f value, there is a p value that tells us the probability that the null is true if we observe that f ratio. So for whatever, so for an f of 1, there's an associated p-value that tells us the probability that the null hypothesis, that there's no difference between the group means, is true. And also, just like in t-test, there is a value, there is an f critical value that corresponds to p equals 0.05, which is the alpha level. How can I change my color? Can I do that? I don't know if I can do that. Yeah, anyway, that if we run a study and we observe an f that is greater than, because all f's get bigger as they go to the right on this graph, if we observe any f ratio that falls into f statistic that falls into this part, which is greater than our f critical value, the probability that the null is true when we observe that f is going to be less than 0.05. And so therefore we reject the null. Whenever we find an f ratio, an f statistic that is greater than the f critical value. Whereas only any f statistics between the critical value, the alpha level, and 0, we fail to reject because p is greater than 0.05. So what, excuse me, what I hope that you've seen, oh, that's how you change the color. The format. Now we understand. So what I hope that you're seeing here is that despite the fact that we have a different statistic, an f, and despite the fact that the distribution of the statistic is not normal, but it's a little, it's like a humpback whale kind of. I don't know if that's, yeah. Anyway, it's like a whale head poking out of the water. That's kind of how I'm thinking of it right now. That even though the distribution of those f scores is a little bit different, the same principles that we've already learned still apply. If we observe a statistic that's greater than our critical value, we reject the null, because as our critical values go up, our p-values go down. Put that another, so I'll just draw it over here. As the f's that we observe go up, the corresponding p-values go down. So larger f's are associated with lower p-values, and if the f is greater than our critical value, that means the p-value is less than our alpha value of p equals 0.05. And so anytime that happens, we say, okay, it's probably not true that these means are exactly the same. We reject the null hypothesis that that all condition means are exactly the same. And I guess that is a nice enough segue to let's just check where we are in the notes here. I'm kind of jumping around just a little bit. That's a nice segue to talk just briefly about the hypotheses. So the null hypothesis for ANOVA is that the condition means are exactly the same. So let's just think about an example, right? So I'm interested. Let's imagine a study in which we want to test people's memory under different conditions. A lot of students particularly, believe that if you listen to certain kinds of music while you study, that will help you remember whatever you're studying better, right? That if listening to music is going to affect your memory. And so we're psychologists. We can test this. We can run a study in which we think, okay, well, maybe the type of music we listen to will affect how we remember things, right? Because a lot of people believe that for example, classical music is a good thing to put on while you're studying, whereas it's probably not a great idea to study while you're listening to heavy metal, or insert whatever desirable type of music you wish there. And so those are two conditions, two conditions of one independent variable. The condition, the listening condition, what you're listening to, right? So as it is, I just described a study in which we would be running a t-test. Listen to classical music versus listening to heavy metal music. But now we've transitioned to ANOVA, in which we need a third condition, right? So metal. A third condition in which people will listen to classical music, heavy metal music, or no music, right? A control condition. So we have an experiment now. We will have people listen in one of three conditions to classical music, heavy metal, or no music. And in each condition, we'll measure, and we'll measure their memory after listening in one of those three conditions. So in the no music condition, people will just sit quietly for however long people listen in this study, in this condition. Is that clear? So the study we're listening to, the study we're talking about is classical music, heavy metal music, and no music. So these are the three conditions of our what people listen to independent variable. And we in each condition, after they listen to some stuff, we'll give them a memory task. So people will study while they listen to classical, study while they listen to heavy metal, or study while they don't listen to music. And then we'll give them a memory task for what they studied, right? That seems like a pretty straightforward kind of experiment. And this would be the case where I'd be asking you to understand that, but this is a very frustrating experience for me because I can't. So I really hope that you understand this. And just for that, I'm just gonna go through it one more time. So people will listen to something, and that something will be either classical music, heavy metal music, or nothing. So call it something asterisk. While studying, right? So studying a list of words. That's a pretty standard kind of experiment in cognitive psychology. People will study a list of words while either music is playing, classical music or heavy metal music, or no music is playing. And then After that, people will complete a memory test. So, well, let's take a brief diversion, because it's oh, it's unclear what the design of this study is. There are two different ways this study could be conducted, right? I could conduct this study, according to what we've already talked about this semester. I could conduct this study in which one group of people listens to classical music, a second group of people, one group of people studies while listening to classical music, a second group of people studies while listening to heavy metal, and a third group of people studies while listening to nothing. That would be a between subject experiment. So I randomly assign people to be in one of three groups. That'd be a between subject experiment. That's one way to do this study. A second way to do the study could be to have each person study under three conditions. They'd study some words while listening to classical music. They'd study other words while listening to heavy metal. And they'd study a third set of words listening to nothing. So each person would listen in all three conditions: listen to classical while studying, listening to heavy metal while studying, listening to nothing while studying. And then they would study while listening to classical and then perform a memory task. Study while listening to heavy metal and then perform a memory task. And then study while listening to nothing and then perform a memory task. So they'd have three separate memory tasks. And that'd be a within subject experiment. Right? So those are two different ways in which we could run the same experiment, right? And so this would be an example of when we would use an ANOVA, because there's one independent variable, what people listen to, with three groups. And because this study could be run either as a between subject experiment or a within subject experiment, that means that there are two flavors of ANOVA that we could talk about, which might make sense because with t-tests, there were two flavors of t-tests depending on whether the study was between subject or within subject. So with ANOVA, if the design of the experiment is between subject, like this description, each person is randomly assigned to one condition of the independent variable. That is an independent ANOVA. aka between subjects ANOVA. Whereas if the study were within subject, that would be a within subject ANOVA, aka repeated measures ANOVA. Repeated measures because people are measured, their memory's measured repeatedly. Once in classical, once in heavy metal, once with no music. Repeated measures of the same DV under different conditions within subject ANOVA. Now, I tend to just call the different ANOVAs between subjects ANOVA versus within subjects ANOVA because that seems easiest to me. So we can definitely just keep that convention because it just seems right and best. Excuse me, I need to adjust a little bit. But yeah, those are the two different kinds of one-way ANOVA that we can have. A one-way ANOVA can be between subject, and a one-way ANOVA can be repeated, can be within subject, depending on the design of the experiment. Right? I hope that was clear. So that corresponds to the right, the two different flavors of ANOVA. Right, the math between the two ANOVAs is slightly different. Right, it's not. I'm not going to get into this, and I'm not going to hold you responsible for this because the book doesn't even talk about repeated measures ANOVA, which I find strange and I understand the decision, but I still find it strange just to completely ignore the fact that it exists. So unlike the book, I'm not going to worry about the math. We're not going to talk about it very much at all. It's different between subject and within subject. Fine. That's something you can learn in grad school because even though the math is different, they're interpreted in exactly the same way. They're interpreted by observing an F value, conducting an ANOVA and getting an F statistic that if it's greater than the critical value will be significant. And that's exactly the same whether the design is between subject or within subject. All right, so there's the two different flavors of ANOVA, and we've kind of been jumping around a little bit. So let's go back down to what the ANOVA actually tests. And this is a little bit, this can be a little bit confusing. Excuse me while I die. Sorry. Bless me. So the null hypothesis is exactly what the null hypothesis has been the entire semester. There's no difference between the means. That the mean of this group, the classical music group, is equal to the mean of the heavy metal group, which is equal to the mean of the no music group. People will remember as many things when they study while listening to classical music as when they study while listening to heavy metal, as when they study while listening to nothing. Their memory is exactly the same in all three conditions. That's the null hypothesis. There's no difference between the means. The alternative hypothesis is not what you're probably expecting it to be. The alternative hypothesis is that there is a difference between these means somewhere, very vague, that one of these means is different, that there is a difference somewhere. What do I actually have written? Not all the condition means are the same. So that's another way just to say the exact same thing. There is a difference somewhere. Not all the means are the same. Now, you might be thinking, I know, so I was saying that you might have thought that I was going to say that all these means are different from one another, that classical music is different from heavy metal music, which is different from no music. That doesn't necessarily have to be the case. You know, I will submit to you that in general, you are better. Let's just put some fake numbers in here. You'll remember more items if you don't listen to music while you study than if you do. It might be the case that listening to classical music will be not as bad for you as heavy metal music, but neither of these are good. It's not good to study while listening to music. It's not good to study while distracted. And so your memory is going to be best whenever you study with no music than either of these two. And so this is what I mean when I say that the means, not all the condition means are the same. Now, I mean, it could be the case that classical music, that it doesn't matter. It doesn't matter what kind of music you listen to. The effect of listening to music is exactly the same. It will damage your memory ability relative to no music. And it doesn't matter if it's heavy metal or it's classical. So this is the case in which the alternative would probably be true, because listening to no music has a different mean than listening to heavy metal, which is the same as classical music. Now, the null hypothesis is that all these means are the same, but the alternative hypothesis is that not all the means are the same, which is not the same. I need to clear some stuff. These are not the same thing. Not all condition means are the same is not an equivalent statement to all the condition means are equal. It can either one of these could be the case for the alternative hypothesis, but it's not necessarily the case that the alternative hypothesis is that all the I wrote that wrong. This is not the alternative hypothesis. The alternative hypothesis is not that all the condition means are different. The alternative hypothesis is that they're not all the same. It could be the case that the one mean is different than the other two means, which are exactly the same. It could be the case that all the means are different from one another. 20 is different from 10, which is different from 30. It could be, but that's not the proper alternative hypothesis. I feel like I've beaten a dead horse. I hope so. So those are the hypotheses for ANOVA. And for the most part, we've talked about this, that we judge an ANOVA is significant if the observed F value is greater than the critical F value, right? Because we have this case in which these means are mathematically different from one another. 20 is mathematically different from 10, which is mathematically different from 30. But the question is, are these means significantly different from one another? Are they great? Is the difference between these means greater than what you would expect by chance alone? Is the difference between these means greater than what you would expect if randomness just dealt you a hand of means. The analogy didn't work. So if they're significant, if the means are significantly different from one another, that means that the mathematical difference that you observed between the means is due to something other than chance. I know it's a little weird and backwards, but we talked about this a little bit. I'm just digging back into something we already talked about. That you observed condition means for some reason other than chance alone. Specifically, that you observed people's memory was greater when there was no music than when there was heavy metal music, because the no music condition is less distracting, possibly. And you observed that people remembered better when they were listening to classical music than heavy metal music, because the classical music is less intense. Or it could be that the classical music doesn't have any words to mess up with learning, right? There's something affecting these means that is systematic and interesting. And we'll get back to this stuff about degrees of freedom, because I kind of started down a rabbit hole on what the F actually is, which is and I want to just return to that, really just to talk about what between group variance is. Now, I'm sorry that Fisher is a jerk who decided to call this type of variance almost exactly the same name as between subjects experiments. Between group variance is a thing. Between subject experiments is a thing. Between subject, between group, different things. Between subject, between group, different things. Sorry about that. If I were to reinvent statistics, I would give them different names. I understand that's confusing. But let me, and then the denominator, so again, F ratios are the F values are the ratio of between group variance to error variance. So variance due to chance, variance due to differences between groups, and over variance due to chance. So let me try to find something real quick. Sorry, I should have had this queued up. I'm the worst. This would be the case in which I'd be drawing something on the board, but it's just not as easy. Well, no, screw it. I can do this here. So let's imagine that we ran this experiment and we observed these means. So just imagine that we graph these. such that this is probably not to scale. How riveting watching me. Right, so this is basic. Okay. Okay, whatever it's gonna do. It's gonna have to do. So sorry, took me a little bit longer than expected. These are the means that we were just talking about. That people's memory scores differed across the different levels of the listening conditions. When people listened to no music, their memory was 30. When people listened to heavy metal music, their memory was 10. When people listened to classical music, their memory was 20. So why am I pointing this out? Because I'm trying to illustrate what between subject variance is. Now, to think about what between subject variance is, I'm going to do something. I'm going to calculate the average of these averages. I'm going to add 10, 20 plus 10 plus 30, and I'm going to divide those means by 3. So 30 plus 30 divided by 3 equals 20. And that is the overall average of this sample. So I'm going to draw that in blue. So we see that, barring we see that this mean for classical music, 20, is exactly the same as the overall average of all conditions. That the memory in the heavy metal condition is less than the average, and the memory in the no music condition is greater than the average. So this is the case. We would call this between group variance. How much the groups differ from the overall mean. The overall mean of the study is 20. And because not all the means were 20, because this mean was 30 and this mean was 10, there's some between group variance. That this mean is not the same as the overall mean, and this mean is not the same as the overall mean. So between the groups, there's a little bit of shifting. And less so than if, for example, people's memory was much greater when there was no music. Now, compared to this condition, there's a lot more between group variance. There's a lot, the deviation, let's make this clear. In this condition, and with these results, we can calculate the average of the sum deviations by subtracting 20 minus 20, which is 0. So I'm going to take that away. I'm not going to get too far into the weeds on this math. The point is that between group variance is how much the condition means differ from the overall mean. The more the condition means, the further the condition means are from, well, I guess this would probably bump this up a little bit. The more the condition means differ from one another, the greater the between group variance. Whereas if all the means, if all three condition means were exactly the same, there'd be no between group variance. Here, all three condition means are the same. There's no between group variance. Here, the condition means are widely different from one another. There's lots of between group variance. And so what F ratios do, what F statistics do, they calculate the ratio of between group variance to error variance. Now, if there is no, if there's no between group variance, as in the second example that we just saw, there's still variability. This is going to be a hard one to wrap your head around a little bit. There's still, all measurements have variability, going back to like day one, right? There's differences in height across people. There's also differences in the why can't I find this word? How precise, the differences in the precision of the measurement of height. We could talk about height in feet, height in inches, height in milliliters, height in millimeters, height in fractions of millimeters, right? There is also sampling error and measurement error. So there's even though when the means are exactly the same, there's no between group variance. There's still there's still variance in these groups, and that's what the error variance is. There's still variability in the responses that produce these means. Because really what I'm trying to point out, so if there's no between group variance, then between group variance is 0. But I told you that the most common F value was 1. You know, I'm gonna what I'm trying to explain to you is a really hard concept, and I'm not doing it well. Ultimately, what I'm trying to build up to is that when the null hypothesis is true, we expect F to equal 1. I was trying to give you a non-mathy explanation as to why this is the case, but I was not doing a good job. This is what I want you to know. I want you to know that when the null hypothesis is true, the F value we would expect to occur is 1. In the same way that when the null hypothesis is true and we have two groups, T would equal 0. It's easier to see why T would equal 0 because T is a mean difference. One mean minus another mean in the numerator. If you subtract those means from one another, you get 0 in the numerator, and therefore the T, when the null hypothesis is true, should be 0. Now, without getting into the weeds on some heavier hitting math, it's not the case. It's not exactly the same case for ANOVA. And so this is one of the times in the semester I'm going to just say, encode to memory that when the null hypothesis is true, that when for the prediction that the condition means are exactly the same, F is going to equal 1. Okay. So I feel like we've gotten a little bit far from what the goal of what we're doing is. Talking about ANOVAs. Talking about 3 means differing from one another. 3 conditions with 3 means, and we're trying to compare whether those means are exactly the same. And so just kind of coming back to that. Sorry. Coming back to that to kind of bring it on home. Something that just to talk briefly about assumptions, just because we always want to remind ourselves of the assumptions of the tests that we're conducting. And these are the same assumptions that we've been talking about all semester. That the scores, each person's memory is independent from every other person's score. That none of the participants in the study were cheating, essentially. That's one way to think about independence here. That everybody's memory was exactly their own memory. That the measurements of the variables is appropriate. That the dependent variable is interval ratio. That memory, the way you measure memory, can be any number of values on some continuum from 0 to however many items people say, and however many items people can remember. And the IV is nominal. So the independent variable is that there are 3 or more, for ANOVA, distinct categories, 3 groups into which people can fall. That the responses in each condition are normal, and that the homogeneity of variance, and that there is homogeneity of variance, that the variance or the standard deviation is the same in each condition, that the variance of the heavy metal group is the same as the variance of the classical group, which is the same as the variance of the no music. Right? So those are the assumptions. And if the assumptions are met and our data meet these assumptions, then we can have faith and trust that the results we find with our ANOVA are likely to be true. And so coming back to when we run our ANOVA, we have a slight, we do have something else that's new. For t-tests, we had one measure of degrees of freedom. And I told you to think about degrees of freedom as essentially the same as, I can't blank on the word, essentially the same as sample size. That for t-tests, degrees of freedom is basically a reinterpretation of sample size. ANOVA is a little bit different. And it has to do with the fact that for ANOVA, you get an F, which is a ratio of between group variance to within group variance, between group variance to error variance. And each of those sources of variance, between group variance and error variance, has its own degree of freedom, which is weird. I'll submit that to you. Completely bizarre for the purpose at which I'm wanting you to understand ANOVA. Basically, though, scrolling down a little bit, this is what the degrees of freedom look like. So for T, you would write up you have one degree of freedom for your T value. But with ANOVA, you have the F instead of the T, but you have 2 degrees of freedom. One for the numerator of the ratio of the statistic, and one for the denominator of the ratio of the statistic. So this is the degrees of freedom for between group variance, and this is the degree of freedom for within group variance. Looking at this actual degrees of freedom here, 2 is the degrees of freedom for between group variance, and 57 is the degrees of freedom for within group, for error variance. I'm going to repeat this. Right here, the first degree of freedom is between group is degrees of freedom for between group variance, and these degrees of freedom are degrees of freedom for error variance. So between group degrees of freedom, error degrees of freedom. And now the question is, how do we calculate them? The numerator degrees of freedom is k minus 1, the number of conditions minus 1. So the experiment we've been talking about through this lecture has 3 levels of the independent variable: classical music, heavy metal music, no music. 3, K equals 3. So the degrees of freedom for that numerator is 2. 3 minus 1. Like that. For the error degrees of freedom, in the denominator of the F ratio, the degrees of freedom is N minus K. N is the number of people in the sample, and K is the number of conditions. So if we sampled 60 people and we subtract 3, because K is the number of conditions or levels, levels is the same as conditions, groups is the same as levels and group, level, condition, all the same word. The degrees of freedom would be 57, 60 minus 3. So that's what the degrees of freedom will look like. When you do the lab, you'll see there's 2 sources of degrees of freedom. And this is how those degrees of freedom are calculated. And so just kind of rounding up this section, we talked a little bit about the looking up the F critical, the observed F value that we find should be greater than the critical value for the F. And just like in t-tests, there's a different critical value for every degree of freedom, for every degrees of freedom that there are. The critical value, the critical t value for 18 degrees of freedom is different from the critical t value for 30 degrees of freedom, and which is different from 31 degrees of freedom, which is different from 32. The critical value, the value that the observed F value we find, depends on degrees of freedom. And just like with t-test, as we have more degrees of freedom, our critical value goes down. So let's scroll down here. As we have more, as our sample size gets bigger, and so this is the appendix out of the back of your book. So the degrees of freedom in the denominator. So the denominator degrees of freedom, N minus K, go down the rows. So as the sample size gets bigger, these, for the same numerator degrees of freedom, the critical values get smaller. So it's the case that as we sample more people, it's easier to find significance. And to find the critical value for ANOVA, we first have to calculate our degrees of freedom and then look up the critical value. So for 60 people and 3 conditions, the degrees of freedom are 257. So we go to this appendix in the back of the book and we try to find, and we find that 2 is in the column right here. And so we scroll until we find 57 in the denominator column row. So there's no exact 57. It goes from 55 to 60, but it goes from 3.16 to 3.15. So for all intents, 3.16, close enough. So this means that if we run this study in which we have people listen to heavy metal music, classical music, or no music, and we sample 60 people, when we run an ANOVA to compare those 3 means, the F value we get from that ANOVA needs to be greater than 3.16. And if it is, we can say that those means are different from one another. That one of those means, that not all of those means are the same. Now, I spent a lot of time trying to convince you of what the proper alternative hypothesis is. Because if we find a p less than 0.05, if we find an f, if we observe an f value that's greater than the critical value, then we know that the means, that there is a significant difference somewhere, that the means are not the same. But the question we really want to ask is, where is the difference? So the means that we observed were 20 for the classical music, 10 for the heavy metal music, and 30 for the no music. And if we find a significant f value for those three means, we want to know what's actually different from what. Is the memory when is memory, people's memory when they studied listening to classical music, significantly greater than memory for people's memory when people studied while listening to heavy metal music? And is people's memory when they didn't listen to heavy metal music, when they didn't listen to any music, is that greater than both when people studied while listening to classical music and when people studied while listening to heavy metal music? That's what post hoc tests help us find. Basically, there are a bunch of t-tests. If we have three conditions, we have three different t-tests we could run. We could run a t-test comparing these two means, mean 1 and mean 2. No, I guess it's not gonna work. We could run a t-test comparing mean 1 and mean 3. So mean 1 and mean 2 would be like classical music compared to heavy metal music. Mean 1 and mean 3 would be like classical music compared to no music. And mean 2 and mean 3 would be like heavy metal music compared to no music, right? So that's what post hoc tests do. After we find a significant ANOVA, we can run post hoc tests to compare each mean to each other, every mean to every other mean, to find where, the significant difference is. That's kind of where we're going to end tonight. There's going to be some practice in the lab looking at post hocs and trying to decipher between the overall ANOVA and the post hoc tests, telling us where the significant difference is. But for now, let's just go over this once again very, very quickly in summary. What's different between ANOVA and t-tests is that t-tests compare two means, ANOVAs compare three means or more. There are, just like t-tests, there are two different flavors of ANOVA. Well, I guess there's a third t-test, but whatever. As in t-tests, but not exclusively as in t-tests, there are two different types of ANOVA, one-way ANOVA. Between subject ANOVA, in which each person is randomly assigned to one group and completes one measurement of the dependent variable, or within subject ANOVA, in which each person is in each condition of the independent variable and completes as many measurements as there are levels of the independent variable. So, and these are for one in IV ANOVAs. Let's go back. In closing, we have this, we've been working a lot this semester with this idea of the flow chart. And so because we now know more statistics, we can add to our flow chart. We always start with what is our DV. Bring this over to my lap so I can type a little bit better. Or you're just going to be looking at my fingers for a little bit. What is our DV, and is it interval and ratio? If it is, we're just going to assume that it is. We're not going to go. So if it's no, we stop. However, if our DV is interval ratio, then the next question we ask is there an IV? If there's not an independent variable, that's a place where we've landed before, in which we need to ask, do we know the population variance? So that's sigma, the funny looking 6 thing. If we do, then we run a z-test. If we don't, then we run a single sample t-test. If there is an independent variable, the next question we ask is, how many levels of the independent variable are there? If there's 2 levels, it's going to be some flavor of t-test, for which we need to ask, is the experiment between subject? Were people randomly assigned to one group? Were the people in each group different, completely separate people? In which case we would run an independent t-test. Versus if it was a within subject, we would run a dependent t-test, or a paired samples t-test, as SPSS calls it. So that's 2 levels. If there are 3 or more levels, then we're in the family of one-way ANOVA. One-way ANOVA because there's one independent variable. You might imagine that we're going to change this flowchart next lecture by adding in a question about how many independent variables are there. Sorry, I'm futzing around. Sorry. If there's more than 2 levels, we're doing a one-way ANOVA. And again, we need to ask. I'm just going to move this over. Again, we need to ask, is it a between subjects design, for which we'll run between subjects ANOVA? Versus, is it a within subjects design, for which we'll run a within subjects one-way ANOVA. So our flow chart is getting bigger. So I hope that you continue to try to break down questions by thinking about them in this way. Always look and ask, what is the DV first? Make sure you understand what that is. Make sure you understand what the difference in what we're measuring is, because that is the first place to start. What are we measuring? What are we talking about here? And then from there, just break it down as logically as possible. Is there a set IV? Yes, either no or yes. Most of the time, there is. In most studies, in most experiments, there's a very firm IV. In which case, then the question is, does it have 2 levels or 3 levels? And at which point, we need to start wondering what the design of the experiment is that will lead us to exactly the right statistic that we need to run in that instance. So that is where we depart for one-way ANOVA. There's going to be a lab that one of my colleagues is going to come help you with. Please, if there's anything in this lecture that was remotely confusing to you, ask me. Right? Send me an email. Also ask whoever is coming down for the lab, because everybody that I'm sending is great. They're all amazing statistical thinkers, and they will certainly be able to answer your questions. So please do not, I really, really, really don't want you to be confused or concerned while I'm not lecturing in the moment and being able to get feedback from you and see you and try to understand if you understand what I'm getting you to understand. So this is a new thing for me, lecturing to a computer screen, trying to imagine an audience. So I'm really, really hoping that you got something from what we talked about. Also, send me an email if that's if you don't understand stuff, but as well, Google is still your friend. YouTube is still your friend. You will find, just like everything else in this course, you'll find hundreds of videos and articles and blogs and explainers out there trying to show you what one-way ANOVA does. So use all your resources to the best of your ability. Very good luck trying to understand this. Please, also this is going to be available to you for the rest of the semester. Watch it over, rewind, go back, do whatever you can to make sure that you're understanding this stuff. And until our next lecture, I will not see you later because I'm not seeing you. Anyway, thank you.